All right, so my name is Nikki Kruger, and I'm the Building Science and Business Development Manager for Therma-Stor. Therma-Stor is headquartered in Madison, Wisconsin. That's where we engineer and manufacture all of our different products for several different brands. We have whole house ventilating dehumidifiers, which is our Ultra-Aire brand. Sante Fe dehumidifiers, which is more basement and crawl spaces or more, dedicated smaller areas. And then Quest is our commercial climate control. So that's our full line of commercial dehumidification equipment. And then Phoenix is our restoration equipment. So anything that a restorer would use when there's hurricanes or a water loss or a fire, we manufacture a full line equipment for the restoration industry. So lots of commercial components going through our factory, and all of those commercial components are also used in our residential dehumidifiers. So you get a really good quality dehumidifier for residential. Therma-Stor came out of a company called Bomatic. So Bomatic was headquartered in Madison, Wisconsin, and was in the dairy industry. So a lot of times, I'll be out at trade shows or on job sites, and people will say, "Oh, DEC," and they're thinking of the dairy equipment company that used to manufacture these dehumidifiers. That's what it was first known as. And so Bomatic manufactured equipment that went into the dairy barns so that they could use refrigeration. Therma-Stor not only is the name of the company, but it's actually one of our brands. We manufacture heat reclaim tanks, and those heat reclaim tanks started in the Bomatic, and they would be in the barns. So when they would generate the heat from the refrigeration to keep the milk cold, these heat reclaim tanks would recapture that heat, and they would basically get free hot water in the barns. And so that technology is still used widely today in grocery stores all across the country, ice skating rinks, a lot of restaurants, the Darden restaurants, so the Olive Gardens, those actually use those tanks to get lead points for their restaurants. So, and that was, the mid 70s that we started manufacturing the heat reclaim tanks. And Ken Gehring is a gentleman that was working for the dairy equipment company for Bomatic, and really was charged with, we have these technologies, and they kind of charged him or challenged him with, how else can we use these technologies? And that's when he then came up with Ultra-Aire. So the first ventilating whole house dehumidifiers was in the mid 90s. And then also Sante Fe was the first horizontal dehumidifiers that are used in crawl spaces today. So basically, Ken started engineering and developing these products, and threw his golf clubs in the back of his car and hit the road and started selling dehumidifiers underneath the Therma-Stor company brand at that time. And it's really just kind of transformed from there with different applications of dehumidification technology used in these different products or these different brands for specific industries.
Yeah, and it's funny. No, I'm sorry, go ahead.
Oh, and so we've always been located in Madison. That's where we are manufactured. We have our manufacturing facility there. And it is pretty fascinating that, when you go on job sites and you see these, whether they're using them during construction, maybe some of the Phoenix equipment during construction to keep the building construction going. So, that subs can come in and the substrates are all, the moisture content's right, and they can keep the subs moving along. Or if we're looking at, a whole house application and just keeping people comfortable and healthy and protecting buildings. So I always like to start with some basics to make sure that everybody understands if we start talking about sensible and latent and what that means. And so the sensible load in our home is what the thermostat is, that temperature reading. So if we set it to 74 in July, in Atlanta, that's our air conditioning temp. And that is the sensible load that the air conditioner is going to try to meet, that temperature. The latent load is the moisture in the air. And so our air conditioners are when they're air conditioning to get to that temperature, they're also addressing some of that latent load to try to remove the moisture as a byproduct of getting to that temperature. And so there's a lot of calculations like manual J that are very important when it goes into sizing our air conditioners, because we want to make sure that we're getting to that sensible temperature, but also maximizing the water removal in getting there. So it's important to know what our manual J's are and that our air conditioning equipment is sized correctly for our homes that we're applying it to, or buildings, in order to make sure that, we are getting the maximum amount of water removal possible when the air conditioner is running. And so, and especially right now, indoor air quality is top of mind for everybody. I mean, more so than it's ever been. Homeowners are more concerned about the quality of air in their home. And we've got a lot of recommendations being kind of thrown out, definitely increase in ventilation, but we're going to have to talk about, that more later, because when we increase our ventilation, that means we're bringing more of the outside in. And that's not just temperature, but that's also moisture. And of course, filtration's a big one, but relative humidity is one that, there's ranges out there. They're saying 40 to 60%. Well, we can't say relative humidity without actually knowing a temperature, because relative humidity or humidity is relative to the temperature. So if we look at this slide here, on the far left, we've got 50 degrees and this exact amount of water is 85% relative humidity. If we do nothing, we have the same amount of water, but just increase the temperature, that relative humidity goes down to 43%. So we need to understand what the temperature is in order to actually understand what the relative humidity is. And this is important when we start talking about bringing in that outdoor air. So if it is, 70 degrees out and 43% relative humidity, and we're bringing that air inside and heating or cooling that air, it's going to change what the final amount of relative humidity is in the house. So we don't always, if someone calls me and says, my crawl space is 70% relative humidity, my first question is going to be, well, what's the temperature in the crawl space? And once we have that, then we can start figuring out, well, what's the dew point? And that gives us a better idea of actually how much water is in the air. So the dew point basically is if you're in a green grass climate, so if you can look outside in the spring, summer, and fall and see green grass, you're what we call living in a green grass climate. And when you look outside in the morning and there's dew on the grass, that means that the air temperature has hit dew point. And we're seeing that more and more we need to really get the trades and homeowners to understand dew point, because there are situations, especially with our air conditioners now, where we have the opportunity to do some overcooling to try to remove a little bit more water, but we have to be careful that we don't have places in the house that can hit dew point. So that's like, if the register starts dripping water, the air's gotten too cold trying to remove more moisture and we've hit dew point. Or ductwork starts experiencing condensation. And in building science, in hot, humid climates, the recommendation for ventilation is to try to put a slight positive pressure on the house with using some supply ventilation, not balanced, but a little supply. And that is trying to stop the hot air coming in, the wet air coming in, to prevent condensation in our walls. So dew point is very important to understand. And we've got a tool that I'm going to show here in a couple minutes. That's an app that's really helpful in understanding dew point. So these things, the factors that can lead to high humidity, actually come from an email that I had to write to a building team. And actually it was in the Northeast. And they had a home that was experiencing high humidity and trying to figure out how to address it. And I think, you know, what we see is when there's homes that are built tight, and I'm not saying passive house tightness, but even just built to code. If you're on, you know, 2018 the residential code, IRC, you're building a pretty tight house these days. And so we've got to look at a bunch of different factors that can lead to high humidity when we're not utilizing a dehumidifier to control it. So first and foremost, tight houses. The whole point of a tight house is to minimize the runtime on the largest piece of equipment in the house. And so to minimize cooling, minimize heating. That's a goal of our tight house, to be able to control our airflows. We have construction drying. You know, if you're in Atlanta and you've had a really rainy spring and summer, and all of a sudden you're closing up a building or a house in the fall, there's going to be a lot of water that's been absorbed by all the materials that are going into that house. And that moisture is going to be released. Usually, I mean, it takes a couple years for that house to start, you know, really dry out from just the construction drying alone. And we know that more houses are being built on slab. And so when you have that amount of concrete, and even if it's a basement, there's a lot of concrete that, you know, you don't get concrete unless you add a lot of water, right? So that's what it's made of. So construction drying is a big one. Lots of wood and other porous materials. You know, we know how popular wood floors are, and of course our cabinets and all that. A lot of moisture. So the low sensible loads. And this really pertains to kind of the shoulder seasons. Dew points can be really high outside in our green grass climates in the spring and fall. And there's no reason to be running air conditioning because it's mild outside, you know, 70 to 80 degrees. We don't need a lot of air conditioning, if any, but there's a lot of moisture outside. So we're not running our air conditioner to remove any water. And then mechanical ventilation. We got to do it. It's code. It should be being measured. You know, we can talk about different ventilation strategies, but the reality is if there are people in the home, we should be ventilating in order to dilute and minimize indoor air contaminants. So mechanical ventilation, if you are bringing in the outdoor air in a humid, mixed humid climate in the spring, summer, or fall, you are bringing in moisture, and it's going to have to be dealt with. Our AC equipment is becoming extremely energy efficient. And when we say, you know, it's energy efficient, that means it's energy efficient at getting to that sensible temperature, not necessarily energy efficient at removing water. And that's what the high sensible heat ratios are. We don't have a lot of dehumidification capacity with our really energy efficient AC equipment. Of course, if you got a crawl space or basement, you know, if you have one of these underneath your house, or you're building houses or working on houses, this is the first areas we got to get right. Bulk water, of course, you got to take care of bulk water. And then from there, we got to look at, you know, the building science is evolving that vented crawl spaces in mixed humid and humid climates really aren't effective, and encapsulating them is probably a good idea. And Advanced Energy out of North Carolina has done a lot of research on this. We've teamed up with them to produce a 2-day building science crawl space class, which is solely on the building science of crawl spaces, encapsulating them and doing it right, because either you leave it the house how it is, or you encapsulate it correctly. There's not really a halfway point that you can do that without creating more of a problem. But we always want to address those areas first. And the reality is, if you've got high humidity in your living space and you've got a crawl space or a basement that's having moisture issues, just fixing those first might help the rest of the house. You might not need a whole house dehumidifier, but that's the first place to start. High dew points and mild temperatures, people generate moisture. Each person generates about 1/4 pound of moisture an hour. Family of 4 is 2 pints or 2 pounds, and that's one term that we should probably talk about. A pint's a pound the world around. So if I say a 70 pint dehumidifier, that's the same as a 70 pound dehumidifier. But a family of 4, 2 pints or pounds an hour. We know that there's our families are home now 24/7. There's a lot of cooking, cleaning. We've got gyms that we've put in our basements or in a room where we're working out. So a lot more moisture is being generated in our homes right now. So we need to think about that moisture as well. And then the reality of it is, we can get as much of the design of that house absolutely, like we were talking about a couple minutes ago before we started, absolutely right. We can get the envelope right. We can get the HVAC system designed right, correctly. But the reality is when people move in, you hand over the control of that house to them. And how I run my thermostat is very different than how my husband runs the thermostat. So if you're counting on them to operate that system to focus on moisture control, that's probably not going to happen all the time correctly. So, and with all these things, you might get a little from the construction drying, you might get a little bit from the ventilation, you might get a little bit from the crawl space and basement, and then people, and all those little bits can add up to a lot. And this is where a dehumidifier really comes in and can control that relative humidity, if it's a whole house one, in the entire home, to whatever the set point is. And in the crawl space or basement, if you have one just dedicated for those areas, again, it's set to a RH, relative humidity, and that's what it's going to try to keep it at. So why homes need dedicated? I mean, comfort, health, and property protection. Moisture is the number-1 detriment to all of our buildings. It will cause microbial growth. It will cause, our footers and the beams and the construction and the crawl space to start rotting, and we can get destruction in our walls. Health. We know that we need to keep our relative humidity below 60% for health reasons. And then comfort, of course. And comfort is typically the #1 complaint. Most people, they don't want to go in their crawl space. So they're not going to see, what kind of destruction might be going on in the crawl space. But comfort is definitely one. And then health. If there's anybody in the home that has a respiratory issue, has asthma, you definitely need to minimize and control that relative humidity as much as possible. So again, all of these reasons are why we need dedicated dehumidification in our homes. And it is the only way to actually ensure. Now, our HVAC systems, if you have a home or you're a contractor and you run your manual J's, you're typically designing that AC system for peak load conditions. So that means The peak load in Atlanta is 92 degrees. So that's what we're going to design our AC system to. And then 75 degrees inside and 50% relative humidity. So 92 degrees in Atlanta. Typically, the manual J peak load conditions happen in most locations 1% of the year. So we design and size our HVAC systems to run at that 1% of the year. And then we got to figure out how we're going to handle the comfort and with temperature and moisture the rest of the year. So it really is the only way to ensure you've got 50%, which is typically what that manual J design condition is. So this is the Sterling chart. Everybody's seeing it out there right now. It really focuses on the health of relative humidity and what our optimum range is. And again, you know, we have 30% here on the low range, which is going to be wintertime. So there's no temperatures associated with this, but we need to understand that 30% is in the wintertime and that 60% is in the humid times of the year. We don't want people in Minneapolis trying to get to 60% relative humidity in January. So we need to understand that these are associated with temperatures and times of the year. But if you look on the left here, these are all the health things. And I'm going to go down there to mites because that's dust mites really. And 80% of the people who have indoor allergies are allergic to dust mites. And as soon as you get that relative humidity to 50%, they die. So it's really important that, you know, in the bedrooms, in all areas of the homes where there, you know, is carpet and mattresses, anywhere where dust mites can live, that we control that relative humidity to that 50% or below, because then dust mites don't live. But all these things, you know, relative humidity is very important. Ventilation is important, filtration is important, but we got to make sure that we're understanding how that relative humidity works. So as we talked about before, advances in high or low or high performance home or low load homes really is advances in low sensible load homes. It really isn't low latent load homes. It's that low sensible. So ACA, the Air Conditioning Contractors of America, have a new manual out. So, you know, they have manual J, manual S, manual D. They have manual LLH, which is low load homes. And it is a manual on recommendations for sizing and designing of our HVAC systems in lower load homes. And so in these lower load homes, we see continuous insulation, driving down our sensible cooling loads, airtight construction, better windows. Now, mechanical ventilation is going to affect our sensible, because if it's hot outside and we're bringing that inside, it's going to affect that temperature in our house. And it also affects the latent cooling. So if it's humid outside, you're bringing that in, which is going to affect the moisture levels. Now, ducts and conditioned attics is driving down our sensible cooling because we're not losing that conditioned air outside of the envelope anymore. We've changed the envelope to the roof line, and we're keeping whatever we're losing through our ductwork in the house. And you know, this chart's showing that that's not affecting our latent cooling, but the reality is when we lost that conditioned air out into the open with our unconditioned attics, our air conditioners ran a lot longer, which also meant we got more moisture removal as a result of that. So it really has, you know, increased our latent loads in our house by not losing so much of that unconditioned or that conditioned air to the outside and running our systems a lot less as well, which is great energy efficient wise. We absolutely want that. But we need to think about the strategy now of how we're going to handle the moisture. And again, we're seeing more and more, especially right now, you know, there's a lot of remodeling going on. in homes. People are in their homes, they realized that they don't have enough room or that their houses are uncomfortable. So there's a lot of renovations and remodeling going on. And if we change one part of the house without thinking how it affects all of the systems in our house, you know, that can definitely affect our moisture levels as well. So if you have somebody come in and they do air sealing and increased insulation in your house, but they left the mechanical system the same and nobody's looked at it and it was already oversized in the first place, it's probably really oversized now, meaning it's not going to be, it's going to be short cycling. It's coming on, running just to get to that temperature really, and it gets to it quickly and then it shuts off. So we're not getting the extended run times we need for water to start being collected on the coils and going down the drain of that AC system. So low load homes, again, low sensible. So this is kind of our definitions of what a low load home is. And so of course we had our rule of thumbs, you know, we've had definitely have seen where we have contractors that, you know, HVAC contractors that pull up to house and kind of do the 2 or 3 looking through it. And that's how they're going to size that, yep, HVAC system. But this is really what we're looking at here when we start getting into our tighter homes. And that is, you know, about that 1,600 square feet per ton. I think the low load homes is at 1,500 square feet per ton is what they're using in theirs. But I mean, that's virtually unheard of, you know, in the 80s and 90s. And a lot of people can't even imagine it. But the reality is if we get that air sealing right, and we get that insulation, you know, that's what we're hoping to achieve, where we're not putting these big systems in, we're putting in smaller systems because we're not getting the temperature differences in the house like we used to anymore. So the ultimate goal in every energy efficiency building standard program is to build a tight envelope to reduce the amount of runtime on the HVAC system to save money. That's the goal. The results is we're using higher energy efficiency ratio equipment, seasonal energy efficiency ratio equipment, so higher SEER equipment. I mean, we've got ductless mini splits out there that are, you know, 30 plus SEER, which is great for energy efficiency. But the challenge is going to be that they can't remove the moisture by focusing on the energy efficiency to get to that temperature. We're seeing a lot of no load to partial load run times, even in hot, humid climates. When we get that envelope right, we are drastically changing the amount of runtime on those systems. And then the more efficient, sensible cooling at the expense of latent capacity, resulting in overcooling to remove moisture. So the system should be set up to overcool a little bit, but we don't want to create comfort issues, and we don't want to create the potential for hitting dew point and developing condensation as well. So we got to be careful on that overcooling. So designing, you know, the IECC 2018 code, the minimum that you can design for cooling is 75 degrees. So when you size that HVAC equipment and you're doing your manual J's, you got to put in 75 degrees. And that's really important to understand, because if we put it at 72 degrees, that's going to change the size of the equipment, which manual J automatically oversizes by 15%. And so we have, you know, as an industry, we have contractors that will bump it up a little bit more, because on July 4th, when there's a huge party going on at the house and people are running in and out and the house can't meet the load, they don't want those calls. So, you know, we got to make sure that we're right sizing, because again, that what they are designing for is still 1% of the time of the year. And we really need to figure out how we're going to design for comfort the rest of the year. So this is a actually updated wording from the new Indoor Air Plus updated standard. So they've always had humidity control in their standard, but this came out, I think this is actually potentially up for comment right now. I'm not sure if that's still up or not, but I know in January of 2021, this was put up for comment, but they've expanded the climate zones. So now they're recognizing that climate zones 1 through 4 probably need to have some sort of humidity control. And then also, it used to say just a dehumidifier or heating and cooling system, and now they're getting more specific into ventilating or whole home dehumidifiers, or the heating and cooling system equipped with additional controls to operate in dehumidification mode. Again, we got to be careful about that dehumidification mode because that is overcooling to dehumidify. So it might not be able to get to that set RH that you want in the home without creating comfort issues by overcooling. And then what we're seeing now, which it's actually very exciting, and this is more of the whole house, but they also have a whole section on crawl spaces and basements as well. But one of the key recommendations that's coming out of the Indoor Air Plus program is humidity monitoring. And they're really encouraging their builders to start monitoring their buildings and homes and multifamily apartments to make sure that that relative humidity is not getting too far out of range for extended periods of time. And then, they're going to have to take action when it happens. So this is a little bit more into the SEER of AC systems. So that's seasonal energy efficiency ratio. So, 13 SEER, 10 SEER used to be our older AC systems. And then now we're getting more, and they use a lot of energy, but they usually were pretty effective at removing water. But now we're really trying to get our systems to be as energy efficient as possible, so our bills are lower. And so these newer, higher SEER systems have larger coils. And so these coils are very efficient at getting to a cool temp quickly, which means less runtime on the AC. And these larger coils hold about a pint or a pound of water per ton. So if you have a 3-ton system, the coils on that system have 3 pints of water. The coils don't get as cold as the older AC system, so less water removed going down the drain. And then they kind of cheat the system a little bit. So when the compressor shuts off because the thermostat has been satisfied, the fan will run 1 to 3 minutes afterwards. So, and by doing this, they increase their SEER rating by 0.5. So they're getting credit for evaporative cooling because all the water that's left on the coils when the compressor shuts off then is getting re-evaporated back into the living space. And that can increase the indoor RH by 10%. So there are manufacturers out there of equipment now that have stopped doing that. And then the other ones, you can shut it off. So if you're in Arizona, maybe not a big deal. But if you're in Florida or Louisiana or anywhere in those climate zones 1 through 4, you don't want that re-evaporation going on. So sensible heat ratio. We are really trying to make sure the industry is becoming more and more educated on the sensible heat ratio because this is the dehumidification effectiveness of the air conditioning equipment. And the sensible heat ratio, that number isn't real common on the data sheets. So sometimes you have to ask the manufacturer for those numbers. And this is some data from a ducted and ductless mini split manufacturer. And just to show here, if we look at this, their 14.5 SEER system has a sensible heat factor of 0.62. What that means is 62% of the BTUs of this system are going to focus on sensible, and 38% are going to focus on latent, so the water removal. So that is a really good piece of equipment for achieving the temperature and also trying to maximize the most water removal as possible. So when the system's running and it gets, you know, a good a long run time on it, then it's going to do a really good job of dehumidifying. But if we look down here at this half-ton mini split, we're at 33 SEER, which means it's really energy efficient, but 96% of the BTUs are going to sensible, and we've got 4% on the latent. And that's because, and if you ever look at one of these, and you can't see my pen here, but I'm holding up a pen, that's the condensate line is about as big as a pen or a pencil. Very little water removal. It's very focused on just getting to that temperature, and it's not going to remove very much water. So we work with a lot of mechanical designers, HVAC contractors, builders. If they are using these high SEER systems, we want to make sure that there's for sure dedicated dehumidification included in the design of that system. So this is some interesting data that was out of that we collected down in Texas, and I think this was in the San Antonio area. But what we're looking at here is, you know, our sensible loads during the day can be, you know, near 90% to near zero most days, meaning we can be at, you know, here we are at 8 a.m. in the morning, and we're probably around, you know, 75 degrees. So probably not a lot of AC runtime. And this is outdoor temperature. So this is the outside. But then as the day goes on, here we are at 4 in the afternoon, and we're at 98 degrees. So our temperatures change throughout the day. And also with that, we now understand that the relative humidity is associated with the temperature. So in the mornings, here we've got the humidity. Our humidity is high. Our RH is high, our temperatures are low, our RH is high, and as the day heats up, our RH goes down. So you think you understand the whole picture here, but the reality is the dew points are the same. So the same amount of water that was in the air in the morning is the same amount of water that's in the air outside in the afternoon. So we really need to understand dew point, because that tells us what the absolute water is in the air. So latent load is fairly uniform throughout day and night. So again, we need to understand dew points to really understand how much moisture is in the air. This is a slide that our good friend Mike Barsick put together and has given me permission to use. And I actually came down to Atlanta, and Mike's was South Face. And I came down to Atlanta, I think it maybe 4 years ago now, 4 or 5 years, when Georgia was looking at requiring mechanical ventilation as part of their building code. And Mike and I presented to the committee, and this was the slide that he put together. And it is very interesting. Oops, very interesting here, because what we have is right here. Oh, shoot, right here we have the manual design load based on temperature. So that's that 92 is our peak load for Atlanta. What's interesting is our ASHRAE humidity design is 82 degrees. So this means that when it's 82 degrees in Atlanta, it's typically when we have the highest dew points. But we're designing for the 92 because that's the temperature. So if we look over here, what Mike did is broke this down in number of hours of occurrences. So 83% of the time in Atlanta, the temperature is 70 to 85 degrees. Probably not a lot of AC runtime. Even, I mean, add the 11%, 94 to even before you get to 90, which is getting closer to the peak load, but still not there yet. So, it's really important to understand that there's a lot of moisture in the air in Atlanta in the spring, summer, and fall, but we can't necessarily count on our AC run times. And as we enforce mechanical ventilation in these homes and in our buildings, we're going to have to think about the moisture that's coming in. And this is really important, I think, for everyone to understand, is you just can't increase the ventilation without thinking about the moisture you're bringing in. As a homeowner, you can't go out and just switch your 50 CFM bath fan to an 80 CFM bath fan and think you can run it all the time without creating other problems. So, no good deed goes unpunished, unfortunately. So we got to think about the consequences. More outdoor air in most climates is going to be a good thing for indoor air quality, but then you got to think about how you're going to condition that air when you bring it in. And that means filtering it, because if we exhaust air, that means we're sucking in air from somewhere else. 1 CFM out is 1 CFM in. So our houses are constantly trying to equalize. And if you're in a humid climate and you're only exhausting out, that means through our walls, cracks, and crevices, we're pulling in hot, humid air through other areas. And it's not being filtered and it's not being conditioned. So in humid climates, we definitely want to think about how we're going to do some makeup air for our exhaust. And exhaust is bath fans, kitchen hoods, we got dryers going on. And if we got all three of those going on at one time, we've got a significant amount of makeup air trying to get in the house from somewhere. And so supply ventilation typically can help that out a little bit. And, here he's got, if you look at this Ultra-Aire unit, and we can bring in outdoor air through the unit. We have a MERV 13 filter in this unit. So we're filtering the outdoor air with that MERV 13 filtration, very effective filtration. And then the house air is coming into the unit with a dedicated return, and that's getting filtered through a MERV 13, and then it's being delivered to the house. So this is some interesting data here that we have. There's a program out there called BOPT that NREL offers for free. And what you can do is you can put in different parameters for a home with different equipment, and it's going to spit out some data here. Let's look at this, what we have here. So this is data based on an 1,800 square foot house built to code in Atlanta, and we are not showing ventilation here. So 1,800 square foot house built to code in Atlanta without mechanical ventilation. And over here we have our relative humidity. So we got 20 all the way up to 80. And then we have the different times of the year, January to February. And we've got different equipment that we are demonstrating on this graph here. So the 14 SEER system is the lighter red. So basically what this is showing us is that 14 SEER system throughout the year on our relative humidity chart. We got May. Oh, we're way over here. Obviously, we got high humidity. It's hard to see the light red there. But during our shoulder seasons, we've got big spikes in humidity here. And it's going to be consistently above that 55. Here we're above 60 all the way into October in Atlanta. So just using a 14 SEER air conditioner, we are not going to be able to control that relative humidity to the design of 50% RH. Now, if we take that 14 SEER AC system and tie it in with a ventilating dehumidifier, which is the darker blue here, you're not seeing any blue above that, much above that 50% at all. We probably got some rain peaks going on here, but not lasting very long. And then we did the same with 18 SEER, which is the yellow, 18 SEER with a dehumidifier. And then, this one's interesting because I hear it all the time. Well, I've got a multi-stage equipment, or I got variable speed. So my equipment is better at controlling relative humidity. And the reality is still 2/3 of the BTUs of that equipment is focusing on sensible, and 1/3 is on the latent. So you're not changing the engineering of that equipment by adding variable. What you're doing is slowing down the fan, creating colder coils, and delivering a smaller amount of cool air to the home, trying to remove more water. But there still has to be a load, a heat load for that to work. So obviously you can see here, we're way out of whack in the shoulder seasons. And even here, it does such a good job of getting to that temperature and maintaining that temperature that it can't get the runtime it needs to actually get the water going down the drain. So, and again, this is BOPT, and NREL offers it on their website for free. The only caveat is it only works on a PC, won't work on a Mac. So when we talked about those green grass climates and dew points, you know, this is Ken Gehring, the man who invented these dehumidifiers, likes to put these dew point maps together and send them out to our team. And if, you know, Ken is very active on a website called HVAC Talk. Has been on there for years answering questions from contractors, homeowners, builders, you know, basically anybody in the industry that is having moisture questions or humidity control questions. And his name on HVAC Talk is called Teddy Bear. So if you go on there and you do a search for Teddy Bear, you will see all kinds of questions and topics that he's addressed and answered. But what I find most interesting is he's the first to tell you when a dehumidifier isn't going to fix it. You know, there's a lot more to think about than just adding a dehumidifier and thinking it's going to control the moisture issues. We really need to make sure that we've minimized the air filtration as much as possible. We need to make sure that the ductwork is sealed, and that everything else is working as close to correctly as we can get it. And then we apply a dehumidifier. But what we can see here is, you know, everybody always talks about, you know, oh, if you live down south, you know, you must need a dehumidifier. Well, the reality is let's say it's August down south and you've got temperatures in the mid 90s. You're probably running, and you got standard construction. I'm not talking, you know, a tight home. You're probably running enough AC during that time to get some pretty good water removal. But if we look here, this is October, and this is the middle of the country, and we've got some pretty darn high dew points going on outside. I mean, not much different than we're seeing here down in Louisiana. And you know, in beginning of October in the middle of the country, you're not running AC. I mean, these are definitely our shoulder season times where it's very temperature wise, very comfortable outside, but we've got a lot of moisture in the air. And I've got another dew point map that shows, you know, this is where we would consider green grass climates. This is where we need to be thinking about some form of dedicated dehumidification, whether it's the whole house or a basement and crawl space during certain times of the year. But I've got a dew point map from September where it shows, you know, 74-degree dew points up here in Maine. And we're seeing more and more where these dew points that we typically only saw in the South are making their way farther north and lasting for longer periods of time. Where it might have been in Maine, you only saw a dew point of 68 degrees a week or two during the year, but we're seeing that definitely changing, and more interest from builders and homeowners up in the Midwest and the Northeast about actually applying whole house dehumidification and not just basement and crawl space. So a friend of mine, Kimberly Llewellyn from Mitsubishi, put this graph together, and it really shows when we're looking at ventilation and applying ventilation and thinking about how we're going to handle the moisture from that ventilation. This is really showing the hours of the year that these areas are in partial load times. So even Miami, I mean, we've got 4,300 hours of the year where we're in partial load conditions. We're bringing in ventilation air, but we're not running our air conditioner potentially enough to handle those moisture loads. So she's got it, you know, all over the place. Some of them get kind of interesting as well, but you know, you definitely, even San Diego, which, you know, San Diego is typically known to everybody as, you know, the perfect climate to live in. But there's can be a lot of moisture in the air. And this is when we're above, I think, a 55-degree dew point, which is what we want internally in our homes, according to ASHRAE. Our goal is to have a 55-degree dew point in our homes, according to ASHRAE, during the humid times of the year. So we get a lot of questions about ERVs. And I know there's a lot of topics out there addressing it, because balanced ventilation is making its way more and more into our standards and our building programs. And an ERV is typically technology that you would use in a mixed humid to a humid climate, because the core of the ERV can exchange moisture. So if it's dry inside and humid outside, and you're bringing in air and exhausting air, in that core, there'll be exchange of the moisture or the latent. They work really well in homes where in the wintertime, where you're generating a lot of moisture, but it's dry outside and exhausting that moisture to the outside. There's a challenge with solely focusing on them in humid climates to minimize moisture from our ventilation, because it will lessen the amount of moisture it's bringing in potentially, but it's always going to contribute to it. And it's always going to depend on how humid it is inside and how humid it is outside. Let me show you some data for that. So this is a house down in Orlando, Florida. It was an NHB Emerald Greenhouse certified, and the homeowners had an ERV in the house, and we're showing partial air conditioning operation here, because we're not running at peak loads where the air conditioner might be able to handle that moisture a little bit more. But here, this blue line is the RH outside, and the green line is the dew point outside. And, you know, our RH here is 60% on this line. And you can see it's consistently over that, the relative humidity in the house, and it's following the dew point outside. And these homeowners were very uncomfortable in their homes. So what we did is then we removed the ERV and put in a whole house ventilating dehumidifier. Again, we got the partial AC run times, extremely high dew points going on outside here. But we just installed the dehumidifier and set it to, you know, 52%, 50% ish. And the dehumidifier is just going to focus on keeping that relative humidity to that set point. So we're not concerned about what the dew points are outside. We're going to focus on keeping that RH inside to where we set it. And there was a study done by Armin Rudd for the DOE. And basically, you know, the conclusion was the ERV is ineffective in keeping indoor RH down during floating hours, which is going to be your morning, overnight times, when the dew points are high, and then the shoulder seasons when there's when the difference between indoor and outdoor absolute humidity, so the dew points, is small. Now here's that app that I was talking about. So we have a free app that you can download from your app store. It is called the Ultra-Aire Psychrometric Calculator. And I'm going to show you here how to use this. So the inlet is what the temperature and conditions are outside. So here, there'll be a little roller here, as you can see down here. You're going to play with this, and you're going to put in the conditions that are outside. So it's 88 degrees outside, and it's 65% RH. it's going to automatically populate what that dew point is. So it is a great tool, if nothing else, just to figure out what the dew points are. The outlet is the temperature I want inside and the relative humidity I want inside. So I want 74 degrees inside, and I play with the RH number in order to get to that 55-degree dew point. So here I've kind of just rolled it up and down a little until I see that 55-degree dew point automatically populate. And then the flow is my ventilation rate. So whether you're using 62.2 or whatever other standard, just trying to figure out what the, if you put in the CFM of your bath fan, you can put that in here. But whatever that ventilation rate is, and it's going to tell you then, based on just ventilation alone and the conditions outside and what you want inside, how many pints a day of water removal you're going to need. So when we look at this, then we got to figure out, well, how much can I count on my air conditioner to remove this? And how much do I think, that I'm going to have to maybe have a dehumidifier do the rest of it? Now, if you click on this eye up here, you can change pints per day to pounds an hour if you want to go more by hour. And then if anybody wants to know more about grains, you can change dew point to grains. But typically in our industry, we use dew point. Grains is typically used in the restoration industry. But it's a great resource. I highly recommend it. And it can, if nothing else, you can just start figuring out dew points. So this is where we actually say, what is a whole house ventilating dehumidifier? So it is a dehumidifier that is going to integrate with the HVAC system in order to dehumidify the entire home. You can actually bring in that outdoor air and filter it. But again, this dehumidifier is going to focus on getting to a set RH. And how it is integrated, this is our recommended install. And so what we like to do for energy efficiency purposes, this install would have a dedicated return to the dehumidifier. And then we would tie into the supply of the HVAC system. So this is showing air handler in an attic. You can absolutely do this if your HVAC system is located in a basement, larger mechanical closet, smaller mechanical closet. We got smaller units. We have 8 units, all different sizes based on your application. And we can probably talk about, maybe sizing a little bit more too later. But then we also have this optional fresh air. You don't have to use a dehumidifier to bring in fresh air. If you are using an ERV or using a different ventilation strategy, you can just cap this off. You don't have to. But you absolutely can minimize purchasing and running other equipment by using the dehumidifier. So what's going to happen is what we recommend is when the air conditioner shuts off and the RH is still too high, that the dehumidifier comes on and dehumidifies the entire house. Now, you can also set it up where I don't care if the AC is running or not. I want the dehumidifier to run anytime that RH is above that set point. And you can set it up that way as well. But this is the most energy efficient way to set up a dehumidifier. Now, that being said, the Florida Residential Building Code was just updated. And as of January 1st, 2021, they only allow 2 installs of dehumidifiers that meet code. So this is our recommended. If you go to our website, we have several different ways that you can install these, because of course, this is great, possibly in new construction, much harder to do in retrofits. And most of the time, our dehumidifiers are going into retrofits to solve a problem. But we're seeing more and more that these are being engineered at the beginning because our systems are changing. But so for Florida, you can do this install. You can no longer do in Florida a return to return install. That has always been our least recommended. Sometimes it's the only one you can do. but they are not allowing that anymore. And the reason being is Florida Solar Energy came out with a study in 2018 on dehumidifier installs, and they concluded that it is the return to return install is the most ineffective and inefficient way to install a dehumidifier. Reason being, dehumidifiers generate heat as a byproduct of removing water. If you blow that heat over the coils in the air conditioner, you are reducing the amount of water that the air conditioner can remove. So that's the first one. We want that air conditioner when it's running to remove as much water as possible. We are supplemental dehumidification. We are picking up what the air conditioner can't remove when it's runs, or when it's not running. That's what we focus on. But we want that air conditioner to remove as much water as possible. So we don't want that heat going over those coils. Second of all, if the air conditioner shuts off and the dehumidifier comes on, again, we're back at that what we saw on that SEER slide, that high SEER, that we're blowing that water that's on those coils and re-evaporating it back into the living space. So again, that's the Florida Solar Energy study. I can definitely send it to you, Matt, and you can have that in the links as well, so people can read more about that. So then we start talking about, okay, well, what about below our homes? We spent a lot of time on, understanding humidity in our homes, but using a dehumidifier possibly to manage that moisture in the house, living space. But what about below? Well, the reality is we really need to focus on what's below our homes. If you have that crawl space or basement, and reason being is 50% of the air in your living space is coming from below the home. So we have to think, and most people don't want to go in their crawl spaces. They don't want to know what's in their crawl spaces. But the reality is what's under there, if it can make its way up through the cracks and crevices into the living space, you're kind of living in your crawl space a little bit there, with the mold and bacteria and insects and all kinds of allergens and contaminated indoor air that's going to make its way up. And it really is going to affect your indoor air quality. So you need to know what's going on below your home, and you can't just ignore it. And this is where we kind of talked about a little bit more about that Advanced Energy out of North Carolina. They did a study on vented crawl spaces, and they were 19 times more likely to experience relative humidity levels in excess of 70% than encapsulated crawl spaces. So a couple years ago here in Northern Virginia, we had 2 Habitat homes right next to each other, same designs, everything. And we went in and encapsulated the crawl spaces. And we know that in building code, there are several different options for conditioning a crawl space once you close it up. And the one that we see most often is using supply air from the HVAC system to condition the crawl space. So in one of the homes, we used supply air to condition the crawl space, and in the other one, we put in a dedicated dehumidifier. And so that supply air strategy basically is going to, the thought is that when the air conditioner is running, it will supply dry air to that crawl space. And again, most of the times that our crawl spaces are probably going to be the wettest is shoulder seasons, or the highest relative humidity is shoulder seasons. So not a lot of AC runtime probably going on. Our crawl spaces are cool automatically, just like our basements. So you're taking dry, cold air and putting it into a crawl space, which if it's 65 degrees in the crawl, and that the RH is automatically going to increase. So for every degree that the temperature rises, the RH goes up 2%. So automatically RH is going to go up. So we data logged the 2 crawl spaces, and after the first week, I had to shut off the alarms for the monitoring system for the one that was using supply air, because it was consistently above 70%. All summer, all fall, it was consistently above, because you're also counting again on the homeowners to run the air conditioning enough to put dry air in there. And these were really tightly built, energy efficient habitat homes. And so they just weren't running the AC very much. So we ended up putting dehumidifier then in that other crawl space. But it was really interesting because, again, you know, just because it meets code doesn't mean it's going to work. And so we need to be monitoring that RH. All right, the big whopper. Well, dehumidifiers use a ton of energy. They're energy hogs. So there's a website out there called Residential Energy Dynamics, and I use it all the time in trainings to help people understand really how much energy our dehumidifier is going to use, because ours are designed to be extremely energy efficient and effective. And that's something we can talk about when we talk about, you know, a big box dehumidifier versus, you know, a dehumidifier commercial grade that's designed for residential. But what I did is I took our 98 pint unit. This is their ventilation electrical usage calculator that they have on their website. And I just took the watts of that unit. So on our website, if you look, every single one of our dehumidifiers, we have what the watts are and on our spec sheets. So I put the watts in there and I said, okay, I live in a humid climate. So for 270 days of the year, that dehumidifier is going to run 20 minutes of every hour. So 270 days a year, that dehumidifier is running 20 minutes. So there's going to be a lot more times where it's not running than it is running, especially in 270 days a year. I put in the kilowatts, so you can put in what your kilowatt price is here. So 11 cents. And down here, it's telling me it's going to cost me $159 to run that dehumidifier 20 minutes of every hour, 270 days a year. And that's the 98 pint one. So again, very energy efficient to use a dehumidifier versus trying to count on air conditioning. So an air conditioner, if we were looking at, you know, equal to equal energy, an air conditioner will run, when it's running, 2 to 3 pints of water, and a dehumidifier will remove 5 to 9 pints of dehumidifier of water. So you're getting a lot more dehumidification for the same amount of electricity when you use a dehumidifier. And again, that's only when the air conditioner is running. That's not being able to control during shoulder seasons or anything like that. So if any of you are familiar with a gentleman named Dr. Joe Steenbrook, this is a quote from him. I was at actually a passive house conference, and he was saying, you know, you're going to probably have to use dehumidifiers in certain climate zones. And, you know, someone stood up and said, well, you know, we can't do that. They use energy. And he's like, you know, 10 steps forward, 1 step back. You cannot energy conserve your way to dry. And that's the same with ventilation. Ventilation and moisture control are going to be an energy penalty. But we have to have comfortable, healthy houses. We can't just focus on, you know, chasing that last BTU or that last dollar. We have to create healthy, comfortable homes. And that has to work with energy efficiency as much as possible. So a little bit more about Ultra-Aire and Sante Fe, our residential dehumidifiers. We have so many sizing options to meet the applications that are out there, from residential to light commercial. We have a 205 pint whole house dehumidifier, which really is used in a lot of light commercial applications. We have an in-wall dehumidifier that we're seeing used a lot in multifamily. And then we also have a split dehumidifier. So if there is concern about the heat that's generated from that dehumidifier, we actually put the compressor outside, so it looks like a mini split, and it discharges the heat to the outdoors, and you get first stage cooling as a byproduct of that unit. So again, 2 very unique units that we have. We do have a 6-year warranty on all our dehumidifiers, and that's kind of us when we were talking about these big box ones I mentioned earlier. When you go to, you know, Home Depot and those, usually they're going to have a 1-year warranty on them. And, you know, I think the best customer quote I've ever heard about our Santa Fe dehumidifiers was not your first dehumidifier, but your last dehumidifier. And that's because people kind of have to go through that, you know, graveyard of Biggs box dehumidifiers where they keep buying them, they end up stacking up, and finally they're like, you know, I'm done with this. I just want something that's going to work for a long time. And so, yeah, 6-year warranty is definitely a huge benefit of ours. Our Ultra-Aire units can help meet the ventilation requirements for anybody trying to meet those. Again, MERV 13 filters, and that's even in our Santa Fe units that are below the house. So, you know, it's going to be filtering a lot of stuff that's below that house before it can make its way into the living space. Energy efficient. We are located in Madison, Wisconsin. So for any technical support that you're looking for, when you call, you're going to get somebody in Madison, Wisconsin. All right, key takeaways here. Houses are becoming tighter and requiring less sensible conditioning, yet latent loads are staying the same or going up. There has to be a sensible load in order to remove humidity with an air conditioner. So, you know, we can set up that air conditioner to run, right size it for longer periods of time, but the reality is you still need that temperature load, the heat load for that air conditioner to run. So you can't always count on it to get to that dedicated RH. Basically, houses work until you put people in them. You can't control how they're going to run the HVAC. And people always want a home that is safe, healthy, durable, comfortable, and efficient. And in a lot of climate zones, you know, I've talked to builders a lot in the past, and HVAC contractors and homeowners. If somebody needed a dehumidifier, fingers started pointing. Somebody did something wrong. But the reality is, if you've made that building envelope as tight as possible, you've sized the HVAC equipment according to industry best practices, you're bringing in that mechanical outdoor ventilation. If you need a dehumidifier, you probably have done everything correctly. And again, it's energy efficiency is always a goal, but you got to think about the comfort and the health of that home as well.
So what is the solution for someone that is looking for a ventilation strategy? Where are they going to make up this air? Is it coming through your system? Do they notice the pressure difference and then automatically comes to your system and is able to condition it when you have that pressure drop inside the house? Like, how does your system help with, like, if you're doing the cooktop, if you're doing the bath fans, and everything at the same time? Like, how does your system integrate with the whole house, you know, balancing it out?
So, you know, we are more about when we are ventilating to try to put that positive pressure. So if you're exhausting in the bathroom, 50 CFM, and it's not time to ventilate with the dehumidifier, because that's we're going to ventilate set up on a time schedule. Then it's probably, you're going to be off balance for a little bit. But as soon as that shuts off, then the dehumidifier, when it's time to ventilate, is going to come in and put that positive pressure back on. Now, there are ways to toggle the ventilation of the dehumidifier with other ventilation strategies, but you might lose some of the benefits and features of the dehumidifier by doing so. So really what we want to focus on is not always trying to achieve a balance, but for most of the time having more of a positive pressure. Bath fan, you know, if you live in a humid climate, you should not be using a bath fan that is running off an RH sensor. Because if you do so, what's going to happen is a vicious cycle in the humid months where it's humid in the bathroom. So the ventilation fan's going to come on and it's going to suck in air through the house to try to make up for that exhaust, and it's going to suck in humid air, and it's just a vicious cycle. That humidity sensor is just going to keep that fan going and going. So if you have one of those, some of them come with a sensitivity option on it, meaning the RH is high, I'm going to come on and then run for 20 minutes or something like that, or just pure timer. But our goal is for the majority of time that we're putting that positive pressure. It might go out of balance here and there. Of course, I mean, if you're going to run a dryer, that's a lot of CFM. Most of the time, you're not going to be able to make that up with a supply ventilation strategy. But once it shuts off, then the house can start equalizing and then doing that positive pressure again.
And I think one point to make is this is much easier on new construction. So when people are talking about like, okay, a dehumidifier is going to take a lot of energy. If you have a tight building envelope, it actually is going to cost a lot less to run this because you don't have as much air infiltration that you have to basically condition with a dehumidifier. And I'm going to just throw this scenario out there for you because, and again, new construction is completely different. I think it's easier to solve these solutions basically with a good design. But when you're retrofitting, most people are trying to retrofit products. And you mentioned like the standalone dehumidifier is not going to work for what you need in most circumstances. You're not bringing that fresh air in. But what if somebody has a new HVAC system, so it's a high efficiency, at least 90% efficient plus, or it's all electric, but they still have that old water heater, and that water heater is atmospherically vented. So if we have a negative pressure in the house and the building envelope is tight-ish, we can have a condition where we're backdrafting. So at that point, do we have to bring in fresh air to the HVAC side? So that's where your makeup air, I wouldn't call it makeup air, but that's where your balanced air is coming in. Or does your system have a way to help balance that, or is it only because it's on at certain times? Because I guess there's certain. I actually lobby against those types of technologies, but if they're in the house, and a lot of times I'm doing a renovation and I come in, it's like, oh, that's really sad. I mean, I see a new water heater and I see a new 80% efficient furnace, and it's like, if I can tell somebody to tear that out, it's like, no, we try to design around it. Unfortunately, it's not a great design to work around.
Yeah, no, and that our system is outside of that. I mean, there has to be a strategy for the makeup air specifically for those systems. We are focusing on the indoor air quality from the standpoint of diluting VOCs and trying to hit 62.2 or whatever other ventilation standard based on that, outside of those products needing that makeup air, because those need designed makeup air strategies for them, for sure. So now one of the things that we often get talked about is sizing a dehumidifier.
Mm-hmm.
And
that makes sense.
Yeah, I mean, like, how much am I going to need? Now, one thing I showed you was, the ventilation app, where that is going to help you based on ventilation. And then we got people. So as soon as we know how much, moisture control we need from our ventilation, then we need to figure out, if we have a family of 4 and they're home 24 hours a day now, then we need 48 pints added on to that for that ventilation. So that kind of gives us, how the pints that we need. And then we, on our website, we have, our sizing is based on square footage, and very, very conservative recommendations for square footage, because it's hard to oversize a dehumidifier, but very easy to undersize. And you don't want to spend that money and not get what you paid for. So we are very conservative. And so if you go, and those are based on like 8 to 9 foot ceilings. Of course, if you start going into 20-foot ceilings and all, I mean, we're gonna have to take into other things into consideration. But for normal circumstances, typical construction, I'm not talking high performance here. I mean, and the reality is if we have a leaky home, we don't know where the air is coming from, but we've got air to deal with. We got moisture to deal with. In a tight home, we better be using mechanical ventilation. We know we're filtering it, but we still got to condition and use that moisture. In leaky homes, probably run an AC a lot longer because they're losing all the conditioned air. Tight homes, not running a lot of AC, but there's a lot of moisture being generated in the house and moisture coming in through the ventilation.
Oh, those are all great points. You also brought up something, the latent cooling load is actually going to go up as people are not face-to-face in school. They're working from home. they need to consider dehumidification and also ventilation strategies more so in their house, more than they would have to worry about before because of the extra time they're spending there. And this is something that I've noticed quite a bit. Like when we've done thousands of energy assessments on houses, and we noticed that the occupied houses, or somebody was working from home, and this is like 10 years ago, this wasn't during the pandemic, that their energy bills are actually a lot higher. So actually living and using the space causes more stress and strain on the space, and your mechanical systems have to do more work. So that's something that people need to definitely keep in mind as like, hey, I want to work from home. It's like, sure. I mean, you're saving on gas depending on your drive time, but you're also, or electric, if you have an electric vehicle, but you're going to have higher energy costs by working from home. And you have to deal with these ventilation issues as well.
Exactly. And we have, one thing that we didn't get into, but, another reason to control humidity in your home is it minimizes the VOC off-gassing of products in your house as well. So, all your cabinets, your furniture, your carpet, everything you bring into your house is going to off-gas some volatile organic compounds. And those basically are indoor air contaminants. And formaldehyde is a big one, is a big one of those, often found. And if you control the relative humidity in your house, those products will off gas at a slower rate. So instead of everything like releasing the Kraken, right? I mean, everything all at once, you're minimizing the off-gassing rate. And that anybody who's got sensitivities, even if you haven't had sensitivities and you bring a bunch into your house at one time, it can cause, like the nose and throat to burn and that sort of thing. A perfect example is Chinese drywall. Chinese drywall made it farther than Florida. But the farther north it got, the harder it was to find, because what was causing it to off gas and cause the corrosion on the HVAC systems was the moisture in the air for extended periods of time. And so when it got farther north, they didn't have that much moisture for that long of time. So it was harder to find the Chinese drywall, which just shows the off-gassing of that Chinese drywall and what it can cause. All right, we'll talk to you later.
All right, thanks a lot for your time. Thanks, Nikki.
Bye-bye.
All right, bye.